So I'm Ron Cogswell, work at Shell in subsurface wells and software HPC optimization group. I'm presenting on behalf of a large cast of characters that will show up in the last slide as a thank you to them. But so we'll start with traditional, I work at Shell. Please use your Evelyn Wood speed reading course. This basically is a disclaimer that says don't make financial decisions based on what I'm saying up here. Because I represent Shell as far as what I'm talking about, but don't make a financial decision based on what I'm saying. Okay, so we're going to have a quick agenda, a little overview of from 10,000 feet what we use HPC at Shell for, and then we'll go on to see a couple slides on the CPU architectures that'll be tested in the benchmarking, and one of my pet peeves about memory bandwidth. Then we'll talk about the micro benchmarks I like to use early on in testing, and then we'll look at some actual production seismic benchmarks, and then we'll go on to a conclusion. So hopefully we can get through this in plenty of time. So Shell uses HPC just like a lot of the other oil and gas companies. We do 80% seismic imaging is going to use our HPC cycles. We're doing shot processing, migrations, model building, iterations on those. And then we do non-seismic, which is a growing area, reservoir modeling, CFD codes. AI and ML is becoming much more popular these days, and they're starting to ask for cycles, and so we're bringing those in. So the CPUs we tested, we had the Skylake, which is kind of our baseline for testing. If you saw the talk last year, that's where we started, was Skylake and Naples. This year we've looked at Rome and Cascade Lake AP. That's what we added to the mix that we're testing. We're still calling Skylake our baseline, because that's what we had at the time when we started these kind of benchmarks. The numbers that we're showing, we're using minimum of 384 gigabytes per node. We've got 40 cores on our Skylake, 64 on Naples and Rome, our Cascade Lake AP, and 128 cores on the Rome system. And most dual socket, that Cascade Lake AP is kind of a, yeah, it's going to show up as 4 sockets even if it's dual socket, because it's kind of a mash together of 2. So memory bandwidth, we've been screaming this ever since, they started going mini-core, multi-core, and so we looked at the theoretical bandwidth and then we measured it with a triad, and we can't ever get to the theoretical bandwidth, but we can measure it, and we're below it. But as you can see, Cascade Lake, 12 memory channels, just screams memory bandwidth. It's great, but there's a balance between memory bandwidth and flops that we're always going to try and do for price performance reasons. So, micro benchmarks. So one of my favorite ones is to look at the cache, and I use this tiny membedge. Just goes out there and shows you where the time goes up, shows you where your cache breaks. And so you're looking at, level 1 cache, layer 2, level 3, and then you get the hockey stick once you've left cache. Right? So on AMD, you've got the CCX, the CCD, and you've got the layer 3. So for a single thread, you're going to max out 16 megabytes. That's the last cache. You're off to memory after that. Whereas on Skylake, you can use all the cache for the layer 3, which is larger and coherent. That'll change, I think, in the future for AMD. We'll see in Milan. So, but big change we were interested in when looking at Rome was the simplification of the NUMA domains, because when you were on Naples, the memory was attached directly to CCX, and you had 8 NUMA domains, and you had to use them that way because that was the only way that you could get to the memory. Now, in Rome, you could go back to using just a simple 2 domains, because you go off chip through the Infinity Fabric and memory is attached there. So you could actually look at 2 domains, but to get the advantage of the cache, you're still going to use 8. We did all the heavy lifting at Naples to do 8 NUMA domains, so we're already there. We borrowed this diagram from the next platform. So compilers. We're not really seeing a good tool chain yet for AMD. We're hoping to test further again this year. But for all these tests, we use Intel compiler. We call it 2019A, which is 2019.1.144 for the tool chain. All the code for the Intel is compiled with AVX 512. And remember, use high, and we stick everything to Haswell for AMD, which is limiting us to AVX2. And internal regression tests between the platforms across our software code worked quite well. We didn't have any deviations that we couldn't explain or we were unhappy with. And we had to disable HDF5 file locking. Okay, so peak flops is one that I like to look at real quick at the beginning, because you can see, for any of your codes that are not using the accelerators for SSE or AVX, you've got it, and then SSE and the AVX. Hopefully, at some point, you're looking at AVX2 and AVX 512. But you can see Rome's got a lot more flops than the other platforms. We'll switch over here for a simple dot product. We try and keep the size within the L2 cache so that we can get the highest flops we can. And so we've got strictly double precision SSE AVX 512 on the Intel platforms, and then we do the single precision. Because if you look at seismic, you really don't have a lot of double precision in the data you're bringing in. It's mostly single precision. So if you can optimize your codes to use single precision, and with these vector units on the CPUs, you can get a huge increase in the number of flops you're getting through. But AVX 512 on the 64-core Cascade Lake AP is getting close to that 128-core Rome on AVX2. And then this one's just thread on the same ddot platform, showing that double precision. We're not seeing a huge jump as we go up there, but if you get to single precision, you get some serious speed up. Okay, so now we'll talk real seismic benchmarks, or from some of our application codes. So in the top left, you see this base platform, Skylake, Naples, there are Cascade Lake, and Rome. So to distill it down, we got about 1.2 to 1.6 speed up on going from Skylake to Naples. 1.2 is probably the closest we'd say. If we go to Cascade Lake AP, basically 2x, because we've got twice as many CPUs as we had on Skylake. So, and then AMD, we've got more cores, but our speed up is basically in between 1.6 and 2. And it depends on the algorithm. And we, of course, filed the serial numbers off the algorithms at the bottom, so people didn't know what we were doing, but you basically see the scaling out of threads, which one of the issues that we'll talk about later is just Amdahl's law shows up when you're just using OpenMP. So a simple ray tracing app, you use a lot of. So lower is better, because the answer the user wants is turn this around as fast as possible. So with this one, it scales with cores. We're not really using a lot of memory bandwidth here. We're just using flops. So it scales with cores. Rome looks good there for us. Then we do a Kirchhoff migration. All the geophysicists, if they were in the room, would know this one, because this is where they do a lot of very simple output-oriented migration. And it's used to be the bread and butter of what we did. Now we do more full waveform inversion and reverse time migrations, which are more accurate, give us better imaging. So this scales primarily with cores as well, a little bit more memory bandwidth required. And so there's the results there. Now we look at a reverse time migration. And so this is pretty much giving us better imaging at the salt flanks and top salt, bottom salt. And you can see the 12 channels on Cascade Lake AP. We think we still got more memory bandwidth issues in our RTM code that we can work on, but they're about equal. The more cores on the AMD is making up for our lack of memory bandwidth on AMD versus Cascade Lake AP, at least for our code. So full waveform inversion, this is the one that gave me the most trouble as a benchmark, because I basically, all the nodes are white boxes. The renewal team brings them in. We got, sometimes we have fabric, sometimes we don't. We got to fit the code into one box, and sometimes we don't have as much disk or what the disk is. So by the time I pull all the disk I/O out of the code, I'm looking at memory bandwidth again. So this is something we're going to work on this year to see if we can't improve that code. But you can see as we move the number of threads up, they all go down about close to scaling evenly with doubling the threads. I get half the time, but we still get a little bit of loss, which is where we're having some issues with Amdahl's law. So conclusions. So we've started looking more at turnaround time on some algorithms. We used to spend all our time trying to pack and get the most efficient use of our HPC resource, but now for the business sometimes it's how fast can we turn this whole algorithm around? Can we turn around this inversion in a day? Right? So compiler choices for AMD, still an issue. We're going to look at it again this year to see. We've got AMD has mentioned they have better compilers. We just want to take a look at them and see how it goes. Memory bandwidth is still critical for our important algorithms these days. Cascade Lake has a lot of memory bandwidth and channels. I'm just not sure that it's going to be cost competitive. With the Rome, the increased cores tended to make up for the lesser bandwidth, and we had a better thermal envelope and rack density with the Rome solution. So here's the list of folks: Adam Hugh, Martin Bozeman's, John Tiesfeld, Nishit Patel, Peter Hogerberger, Sebring Rinker, David, his team provides all these boxes that we get to play with and test. And so the last slide, I'll just leave up some developer comments, and people can read them, and I'll take questions. Well, you can just leave that up there so you can read. Hey.
Okay, a couple of questions in the middle.
Nice job. Your issue with Amdahl's law, have you considered making the size bigger to go with the number of threads?
That's like one of the things when we get to a production size system rather than white boxes, we might be able to address some of those. But some of it's still going to be in the code where, if you just decorate with OpenMP, sometimes you're just, you're going to lose something there.
Hi, thank you for the talk. Addison Snell, Intersect 360 Research. I was intrigued by your chart that had the 4 different graphs that showed algorithmic speed up relative to Skylake. And I want to make sure I'm interpreting this correctly. I noticed that in all 4 of the charts, there was a drop-off in how much performance improvement there was versus Skylake, the more threads we were looking at. Is the implication that Skylake did a better job scaling to more threads than any of the other processors you were comparing it against?
The number of threads for Skylake is smaller, I think. Let me go back to that to make sure. Yeah, because Skylake we're topping out at 40. Here we're scaling all the way out to 128 and 64.
So it's not comparing to the same number of threads?
Yeah, the only ones that compare the same numbers are the 4 and 4 for Skylake is the only one that's the same in all the graphs. Is 4 threads. The first one, the dark blue, and then we just go up to 10, which is a full socket. And over there, it would 16 is a full socket.
Very helpful. Thank you for the clarification.
Sure.
Okay, any more questions for Ron? If not, thank you very much.